Good evening, everyone. Good evening. By show of thumbs up, can you guys hear me, please? Okay. I think we can now start. I think we can now start. So, uh, so we'll continue from where we left in our last class, which was last week on Thursday. So last week on Thursday, we did have an introduction to ML, and I did introduce. I'll be covering the regression models for our first class. We didn't manage because it was quite a long. It's quite a long class that we have to do some sort of data preprocessing and cleaning before we can go about the ML model and see how these models behave differently when you've processed data and when you've not processed data. And that also implies for data cleaning. For a recap on what we covered in our previous class, we did have the importation of the necessary libraries, whereby we had the NumPy as NP, we had the pandas as PD, of which both of these are responsible for data manipulation. We did also have the importation of matplotlib.pyplot as PLT for data visualization, same to Seaborn. And I did say that I was going to make use of an inbuilt dataset that comes with sklearn. And from the sklearn datasets folder, we are going to retrieve our Fetch California housing dataset. Then I did some sort of like a follow-up to go about what we have as a DIR in our folder, that is the datasets, and you are able to see where I got the California housing dataset. And you can see here we have the California, but for our case, you are more interested with the Fetch California housing dataset. So these are some of the datasets that you can make use of. I'll be making use of most of them as we go by. Same as to I will be sharing more datasets for us to make use. Then we loaded our dataset just to demonstrate how the dataset is being stored in sklearn or rather sklearn. And the variable name housing or rather the container housing, and upon printing it out we saw how it's arranged in a dictionary array whereby we have the x variables under the dictionary key data. We had our target being aside, then of course the target names and everything that entails as the feature names, which are also the column names of our dataset. And I did brought about the concept of pandas, whereby I said you can't really analyze data that's in form of arrays, and for you to go about it, you need to convert the data into a data frame, or rather a tabular, because most of the attributes that work with pandas only handle data in form of tables. So we had our pd.data frame, which is responsible for the attribute responsible for the conversion of our data into a table. Had our housing.data, that is the mapping that we are retrieving the array.data in the dictionary key.data right there. Then we are getting our feature names to go about. Then we realized that we needed also to do a creation of a new column, that is the target. So some sort of like a merging, but we are creating a new column under the container data. So we went about to explore the data, whereby we inspected the first 5 rows by making use of the data.head function. I sought how to the column names that you have in your data set. Then we add the data types and also the associated column names. And you can see here we add the data.info, whereby you're able to see the column names in the data set and the associated D type, which means a data type. Then we want about to see the description, the summary, the statistical summary of the data set, whereby I made use of the .describe function. Then I checked for the shape of the data set, and you can see here we have 20,640 rows and 9 columns. Then I checked for the nulls, of which these are now the missing data points in the data set. And in this case, I'm checking for the summation or rather the summary. So I should be getting a number if I have. So if mail ink, for example, we had a missing data set, let's say 2, then you'll have a summation of 2. But here we can see our data set doesn't have any kind of missing data point. So it draws me to the next common EDA that you should be also be doing, and that is now the IQR. So IQRs are usually for the sake of outlier detection in your data set. So allow me to share my screen, then I can demonstrate a bit of on how you can check for outliers in a data set. That is first through a box plot, and we'll do an algorithm. In this case, I'll be doing a function to handle it. So we'll have to create a function, then we can have all the required steps on how we're going to do our IQR, that is the interquartile range. So I'm sharing my screen, then I can take you guys through box plot with outliers, because that's the simplest way in which you can see the outliers in each of the columns of a data set. So we have outliers with box plots. So let's say you're visualizing a box plot. Let's say you're visualizing a box plot of a specific column. So how to detect outliers per se has to be about the data field. Of course, the data field now here is the column name. So for me to be able to know that my data set has outliers, I have to focus on the column name, or rather the data field that is storing those specific values or data points. Now, typically a box plot will look like this. So you'll have this right here. You'll have this right here. And when you have that right there, then at some point you can have some sort of like a data points coming about to be this way, Now these are what we call the outliers. Okay, so these are what we call the outliers. Now, why do we detect outliers, or rather, why do we clean out outliers? Because some models are affected by outliers. So outliers may tend to make your model overfit. By overfitting is whereby you have the model not performing as to its potential, but it's overperforming, because now sometimes it can come about with a quote unquote hallucination whereby it's making predictions that are out of the norm. So you need to control by mostly making sure that the model is being trained by a data set that does not contain outliers. Now, this being a typical box plot, so at the top here you'll have the upper bound, then at the bottom here you'll have the lower bound. Now you have the lower bound and you have the upper bound. Now it means for my data set not to have outliers, it needs to be in this range. So this is the range of data points without outliers in this case. Now, with my range of data points without having outliers being there, then it means that my upper bound will be the 75th percentile. Then here I will have my 50th percentile here. Then here I will have my 25th percentile. Thus drawing us to an IQR having the Q3 minus Q1. Okay. of which we're going to calculate our Q1, we have to get our Q2, we have to get our Q3. So typically the 50th percentile is also referred to as the Q2. Any questions?
Which one is the Q1 and which one is the Q3?
Q1. Hello?
Yes, you said the IQR is calculated by Q3 minus Q1. So I was asking which is the Q1 and which is the Q3.
So Q1 is always the 25th percentile, Q2 is the 50th, then the Q3 is the 75th. And this one is usually the median. So this one is the median. So you can get all these stats from the dot describe. So you saw from the dot describe, we did have for each of the columns having the 75th, the 50th, and the 25th. So you can also get those values from there, but there is also a formula on how to go about it. Are we together? Are we on the same page? If I can proceed. By show of thumbs up. Okay. So we'll get back to our notebook and then we can see on how we can detect outliers by making use of a simple function. So do we all have this notebook right here? Do you all have this notebook right here, the one for introduction? Can still share it. Can still share it. If you feel like you want to follow, then type on later on. Still share it here. So what you'll do is once I finish typing, let's say a code and execute that specific code, once you've opened the link, then you can keep on refreshing and you'll have the same notebook as mine. So it's kind of like a viewer interface. So you'll only be viewing, but you can't edit. I'm the only one who can edit. So you refresh to see my updates every now and then. That's for those who don't want to type side by side. Please confirm if you can open that link. Now, for you to have your IQR in place, of course, you need the dependencies, that is the pandas. You also need the matplotlib for visualization, and you also need the seaborn maybe for visualization if you want sophisticated. That is our visuals. Now, we've already loaded our dataset, and right now we're working with the variable name data. So I'll be moving forward with the variable name data right here. So outlier, Lavi outlier detection, and cleaning. Okay, so what we're going to do is we're going to create a function to detect outliers in all the numerical columns. Now, outliers will only work for will only work for numerical columns, the columns that have the either float or the integer data types. Now, I'm sure some of you have already covered the encodings. So don't cover outliers while you've encoded. So outliers should come first, then you can do the encoding, because remember the encoding has nothing to do with uh, being detected as outliers or not. So in case you've done encoding, that is the conversion of a string data type to a numeric, uh, please you have to revert back to where you had not done the encoding, just maybe a cell before it, then you can perform your outlier. So I'm going to create a simple function right here, and maybe if I can explain the function in layman's language. So you can have, let's say, a function to add two numbers. So you can have maybe def. So def is the keyword for a function. Then you can say here maybe add as the name of the function. So def is the function to defining a function in Python. Then add here is what I'm doing is I'm creating a function, but I'm also tagging it with the variable name add. Then after that, I can have it accepting two variables. So you can say maybe a and b. And since it's a function, I'll have my full colon. Then I will enter. Then I will return a and b. So it means that when I execute this, already I've created a function that will be accepting values that will be stored in A, then in B. Then if I want to make use of this function, I will just call it out by its variable name, which is add, open up my parentheses, then I can provide my A and B's. Maybe I can have 3 and 7. So at the end of the day here, if I execute this, I'll get a 10, meaning that my function that is called add, the one that I've just called, when I was creating it, I did return that is now the a plus b. So the returning of the a plus b means that the variables that will be accepted in a as a container and the variable in b will be used as a summation. So typically functions are there to help you to automate your work. So you don't have again to, if you want to add another two sets of values, you don't have again to rewrite an algorithm that will add them. So what you do is maybe you go about to edit, then it will give you the whatever endpoint of what is expected of the function. So I'm sure this was covered under functions in Python. So it's just but a recap. So we're going to create a function right here. So not now that we know, and my function will be going to accept a data. So we'll have def. Then my def will have will have a function with the name detect underscore outliers underscore iqr. So I'm going to name my function this way, and it's going to be accepting data. Okay. So remember data is my container that is storing now my data that I had converted from an array to a table. Okay. Now after having that, I'm going to create outlier indices. So I'm going to create an empty dictionary. So I'll have outlier underscore indices, and I will create an empty dictionary at this point. So I've already started to give instructions to the function that I've just called it detect underscore outliers underscore iqr, which should be accepting whatever that is in the variable name called data, which is our table data set, California housing data set. Now, since outliers are there to detect the out of norm data points, that is based on the upper bound and the lower bound, are specifically for each of the columns, I need to do this for each of the columns. And for it to be in a for it to be in a precise manner. So I'll have to bring in what we call now the for loops. So the for loops are there to iterate, to treat each of the column names as individuals. So what I mean is when we want to print out the column names, you have just data dot columns, right? So when you have data dot columns, you can see the output is a list. So this means that this is already a data that has been structured. So they're being considered as one. For you to treat each of these elements or other items in the list, that the meeting, the house age, average rooms, now you go about the for loop. So you can have something like for I in data dot columns, then you print now the iterated, which is I right there. So you will have treated each of these as individuals. Output will be in a in a in a vertical output, meaning that there is no kind of relationship of a data structure, unlike the first one whereby we have the data dot columns. Now it brings me here, so whereby I'll be doing my for loop so that now I can be able to access each of the columns and go about to calculate my IQR. Here we'll have a simple one, so I'll give a call in. Call is the new variable name that will have the iterated names of the data types, I mean the column names. Then I will have in data dot select underscore B types. Now, remember IQR works for numeric data points. So I should be in a position of whereby I'm controlling my outlier to be only accepting either float, which are numeric data points that contain decimals, or integers, which are numeric data points that are full numbers. So we only have two numeric data types, that is the float and the integers. So for me to have this, I will have the for call in data.select underscore d types, I'm going to only include, I'm going to only include, I'm going to give a list here. So I'm including only float 64, and also I'm including integer 64. So 64 is the format of the bit, then dot columns. Okay. So all the columns that will have a data type float or data type integer are the ones that will be passed into our iteration. So they'll be treated this way as individuals to go about to check for the outlier. So remember, this is a conditional statement, so it should end with a full colon, then enter, and it will indent for you directly. Now, after doing that, you need to determine your Q1, and also you need to determine your Q3. So we're going to have our Q1 right here. So our Q1 will be data that will be retrieved from the call, which is our new variable name, that will have our columns being treated this way as individuals. So data.call dot quantile 0.5. Okay, so this will help me get my 25th percentile. Then I will have my Q3 going about as data call dot quantile 0.75. Okay, now to get our IQR should be Q3 minus Q1. Then for me to calculate the lower bound, the lower underscore bound, I will have this as Q1 minus 1.5 times the IQR. That way. Then for me to calculate also the upper bound, now I will have this as Q3 plus 1.5 times the IQR. Any question before I can proceed? Anyone who felt something is not clear? I explain. Are we together by show of thumbs up, please?
Hello, I'm a bit lost with the 1.5 times IQR.
Okay, so the 1.5 times IQR is a syntax. It's like the pi, 3.142. It will never change. So the 1.5 is what we use. Then the IQR, we are getting it from Q3 minus Q1, whereby Q1 is being gotten from the dot quantile. So this is an attribute in IQR, which is inside pandas that will treat the 0.25 as 25th percentile. Then you'll get your Q3 from the quantile 0.75 because the Q2 is 50. So you don't need the Q2. The Q2 is the one that is 0.50. Are you together, Rashid?
Yes.
Now, for a dataset to have outliers, it needs to be above the upper bound, then it needs to be lower than the upper bound, or rather less. I mean the lower bound. So what I mean is this. Let me need to share my screen. So we had said that these are our extras, our outliers. So this is what we regarded to as the outliers. Outliers. Now, for you to detect an outlier, considering this is our upper bound and this is our lower bound. For you to detect an outlier, the outlier has to be greater than the upper bound. Okay, and for this it has to be less than the lower bound. Okay, so this has to be less than, this has to be greater than for you to detect an outlier. But for you to remain with the clean data, so this has to be less than the upper bound but greater than the lower bound. So they interchange. Are we together? Okay, so outliers are greater than the upper bound but less than the lower bound. Okay, clean, I mean no outliers. They have to be less than the upper bound but greater than the lower bound for you to fall in between here. Are we together? Anyone who hasn't understood? Anyone who hasn't understood? Okay, so get to our notebook. Yes?
Does it mean that for all the continuous data that we'll always get, we trim the whatever is above 0.75 and whatever is below 0.25?
Come again. You are breaking.
I mean, for all the continuous data that we'll ever get, do we have to trim whatever's above 0.75 and whatever's below 0.25?
Okay, so now for this class, we are working with machine learning models. So, machine learning models, we have models that are prone to outliers and models that are not prone to outliers. Now, when we get to the clustering models and all, they are not really sensitive to outliers, but regression models that are sensitive to outliers. In the case you have outliers in a data set, they affect how the model will perform. So the best way on how to cap, whereby you already know that for a linear regression or rather for regression models, the target variable has to be a continuous. It means that you're working with linear data, okay, or rather discrete data points. So it means that you have to handle the outlier such that your model can have some sort of confidence. But when you get to models like the clustering models, which are only associative with features, then when you saw when we are covering unsupervised models, uh, they are not prone to outliers. So if you handle outliers or if you don't handle outliers, it doesn't really matter at that point. So our focus here is to try to come up with a model that we can really rely on, and we are trying to tick our boxes of the perfection of the model by making sure that the model is being trained by precise, clean, and consistent data. Are you together, Rashid? Okay. Okay, Marie. Mori.
So I think listening to the question that has just been asked, I think I might have a little confusion. I need you please to clarify something. Is 0.75 this and 0.25 the same as upper bound and lower bound? Because I the way I was understanding it, I thought the outliers are above upper bound, not 0.75. And yes, and below the lower bound, not below 0.25. I
Okay.
don't know if my question is clear.
Yeah, it's clear. So I want to
Thank you.
challenge you. So I've plotted this. So I have, let's say, 10, I have 20, I have 30, I have 40, I have 50, I have 60. I've plotted it in my box plot this way. Okay. So it so happens that here I had, let's say, I had 10 here, I had 20, I had 30, I had 40, I had 50, I had 60, I had 70, I had 80, and I had 90. So if my box plot gets to be plotted in this case, okay, so which is our outlier here? It means that our outlier is 90 and 80, okay, because they are greater than this upper bound, okay, and it means here that my outlier will be 10. So this 10 right here, because it's less than the lower bound, which is my lower bound here. So it doesn't fall in between here. And for you to get your lower bound and your upper bound, of course, you have to calculate your Q1 and your Q3, that is the interquartile range. And that is associated with the 75th percentile, which is now here. Then here we have the 50th, which is of course mostly the median. Then here we have the 25th. So your IQR should be Q3 minus Q1. Mori, is that clear? You still raised up your hand. Is it a thumbs up? Or you still have a question?
Sir, actually, my question was, is 75 percentile the same as upper bound, or and is 25 percentile same as lower bound?
Okay. So let me.
Because when we were calculating in the formula, the lower bound was like 25 I mean Q1, it was like Q1 minus 1.5 times interquartile range,
Yes.
which means Q1 and lower bound, they are two different things. I don't know if I understand this well. There is lower bound, there is Q1. But in the image there, I think you wrote Q1 at the same level as lower bound. But here, when we are calculating, you calculated Q1 is here and lower bound is calculated here. And there's a difference between Q1 and lower bound. There's also a difference between Q3 and upper bound.
Okay. But you need.
So in the demonstration, I wanted to see in the demonstration, I don't see the difference, but in the calculations in the formula here, I see the difference between Q1 and lower bound and Q3 and lower bound. So in the picture, in our history, what is that in our
Blackboard.
box plot? In our box plot, yes, that is where I want to see where is the lower bound, where is Q1.
Oh, the Q1 is at the top. The the upper bound. You see, you have to get the upper bound from the Q3 1.5 times IQR, whereby you need the Q3 first and the Q1, and you get your Q1 from the quantile, the formula dot quantile 0.25, and your Q3 from the formula dot quantile 0.75. So for you to get this IQR, such that now you are able to cap, so that you are able to slice what is below the lower and what is above the upper. So you first need to get your Q1, you need to get your Q3, subtract, then come about and determine now the lower bound from the box plot. So the box plot was there to show you how to identify a lower bound when you're plotting and how to identify an upper bound when you are plotting. Are you together? Yes, Mbide.
Hi, Tony.
Hi.
Mine is just a request to maybe repeat from the def detect underscore outliers underscore IQR. That bit detects outliers from the data. Then outlier underscore indices equals the curly brackets. Maybe you can explain maybe each I don't know, each row. Each row. Yeah, each row.
The whole function.
Yes, please.
Okay. So when I started the class, I started by saying that we're going to define a function, and our function will be called detect underscore outliers underscore IQR, and it's going to accept what we call our data, which is now the variable name that is storing our data. Then I created an empty dictionary right here, which will be getting back to it so that you can see why I'm having. But now the real work of the outliers come about here, whereby now I'm iterating through columns, whereby I'm selecting specific columns that have the data type either float or integer from the dot columns formula. So once I do this, the selected columns will have to be treated as independent this way. Unlike when you have it as the dot columns, you can see we have as a list. So it means that I'm able to handle them as individuals. So I'm going to make use of the IQR detection. So I need to calculate my Q1, I need to calculate my Q3. So whereby I'm having the data.call, it means that the iterated column, the current one, will have to be passed through the quantile 0.25, because remember you are detecting outliers for each of the data fields, and by data fields these are the column names. Then again, we come about to the data.call for the quantile of 0.75 for the Q3. Then for you to get your IQR, it has to be Q3 minus Q1 for you to determine the lower bound, which is Q1 minus 1.5 times IQR. Then for the upper bound, it will be Q3 plus 1.5 times IQR.
What's 1.5?
1.5 is a standard for it. It's like the pi of 3.142. Yes, yes, Joanne.
If you go, okay, I have a question. If you go to I could be wrong. If you go to the diagram that you had drawn, could it be that Q3 is actually the top of the car box itself, and the Q1 would actually be the bottom of the box that you had drawn in between? That way, the box plot representing that um, that box itself representing the IQR, differentiating it from the lower and the upper bounds.
Okay, let me share. Let me show me. This one.
Yes. So in our case, for example, the Q3 could be 50 where the K50 is. And the Q3 could be where the 50 is. The 50, the top, just like the top of the box. And then our Q1 in this case could be, I think, 30.
Q3.
Yeah. So Q1 being at the top of the box. This box, the box, no, not that one. The box itself, the box that you draw. Yes. And then Q3 being the top, and then Q1 being this one, the line where, yes. And then now the upper and lower bound being the minimum and the maximum. That you're differentiating the IQR. I could be wrong, but that's my guess. That's how I'm guessing we have the 1.5 coming from.
Yeah, you're right. Still right.
I think it's because during the representation, the upper bound looked like upper bound is equals to Q3 and the lower bound is equals to Q1. So I think that's the confusion that Limpo was trying to address.
Yeah. But for you to determine your upper bound, you still need the Q3, this one. And for you to
Yes.
determine your
So
lower bound, you still need this one.
yes, so upper bound is not the same as Q3. They are two different variables. That's my understanding from our box plot.
Yes, Maury.
Oh, yes, she's just clarified everything. This is what I really wanted to understand. Thank you.
Okay. Anyone else? Okay. So we can proceed and see whether we can build the model. Anyone else? Please don't be left behind. Okay, so we have our lower bound calculated, our upper bound. So what you're going to do now is to detect the outliers. So whereby we'll have our outliers. So sorry for the caps. So whereby we have the outliers coming in as so we have outliers equal to data. Here I'm focusing with the column, lower bound, and upper bound. Okay, be careful with the brackets. So you're supposed to select data for that column, lower bound, and has to be greater than the upper bound. Yeah. Then now we can have our outlier indices, outlier underscore indices coming in as for the column equals to outliers dot index dot to list. Then we can use the F string and have that particular column being referred to with the length of the outlier. This prefer this one. And so now we can check for the outliers. So to check for the outliers, we'll have now our outlier underscore dictionary equals to detect underscore outliers underscore IQR, which is the name of our link will accept data. And those are the number of data points we have as outliers. You can see for the column Med Inc., we have 681, house average 0, average rooms we have 511, bedrooms 1,424, population 1,196, the average occupation 711, and the target 1071. Are we all there? By show of thumbs up. Before we visualize them using a box plot. By show of thumbs up, are we on the same page? So let's visualize each one of them. So visualize each of the columns. So I'm going to visualize each one of the columns and let's see where those outliers are detected. So here we'll have num underscore calls equals to the df dot select underscore details. We're going to include again the float. I'm going to include the float 64 and also the int 64. Okay, and this is also associated with the dot columns to get those specific columns. After doing that, I will create a figure, a whole figure that I'm going to subdivide. So we'll have plt dot figure, and we'll have it in the figure size as I'm going to have it as a 15 by 20. So the fig size will be 15 by 20. So the fig size equals 15 by 20. Then I'm going to subdivide it to accommodate our specific columns so that we can be able to see. So for this to happen, I'm going to do a enumeration. So for I and also for the column, in enumerate that is the number of columns. Remember, it's a conditional statement, so we'll have to have a full column so that we can have plt dot subplot. Can do 4 by 2. How many columns do we have? 1, 2, 3, 5, 6, 7, 8, 9. So we can do a 4 by 2 and 1. So 4 by 2 I, and so make use of the SNS dot box plot, and I will have it picking the data from the df column. So my x will be the column itself for it to be plotted. Then I'll have the title, so plt dot setting, whereby I make use of an f string and come about with the box plot. of that particular column name that is being plotted. And because it's already a predefined column name, I'm picking it as a variable. I'll have to have it in curled brackets. Then we can have plt dot type underscore layout. Then I will plt dot for supposed to be data. Sorry, DF is in my head. So 4 by 2, we're getting now must be an integer. So we're missing 4 1. So let me have them extended. So you can have a 4 by 3 to accommodate. So you should be seeing the visualization of your outliers and of like this way. So I'm having a whole figure, then I'm subdividing the figure into 4 by 3, meaning I'll be having those 3 columns to accommodate each of the column names. And you can see the column names are 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's a 4 by 3, making it a 12. So we are in the range of the length of the columns, which is 9. You can see all of them, they've been plotted out. These are now the outliers. So you're able to see the outliers coming about, extending in there from the upper bound and also the lower bound. As you can see here, we have some sort of like a lower coming about. You can see the ones that latitude, longitude, they had 0. So let's see. So they had 0. So you can see also in the visual, they don't have outliers. So that's how you visualize outliers by making use of IQ1. Any question? Questions?
So I have a question on the previous one where we were listing the indices for the outliers.
Mm-hmm.
What could be the reason why mine did not list the indices? It just, the code just ran, said complete, it didn't bring any error, but I didn't get the list like yours.
So if your function is an issue, even when calling it, it will become an issue. So check on your return. So your return should be in the same line as your for, the for here, this one. So check on your return mostly, or rather your indentation after the control statements like before, or rather the def. So mostly the error will be associated there. So it's trying to figure out the steps after after you define the function, but in between it's losing the logic. So you check, then you make sure that it's the same as mine.
Oh, but I'm not getting any error.
Yeah.
It's just the code run says completed, and then I'm not getting an output either.
Yeah, the thing with functions, they won't give you an error most of the time. So it will just
Oh,
execute, but it won't work.
oh,
Yeah,
okay. Let me check again then.
times.
Thank you.
Yeah. Anyone else? Yes, be then.
What could be the reason for the difference in the outliers? Because when I look at your outliers and mine, they are different.
The plotting.
Not even the plotting,
Mhm.
the number,
Uh,
18. Yeah, yeah, there.
how many do you have?
19959.
Same as this data set. The fetch.
Yes,
Did you use the fetch or the housing? Because there are two.
I copied the code that you on the link that you shared.
Okay.
Yeah, the Fetch California.
Share your screen, I see.
Yes.
Share your screen, I see.
Okay.
One. Okay, let me see. Just scroll. Make the function be in the middle of your presentation. Let it not cut. Yeah, yeah, okay. Anyone else experiencing different values? Okay, so
Chris,
outliers.
uh,
So you can see when you're visualizing your outliers, if both of them they're lower than the lower bound and also lower than the upper bound. So it should be greater than the upper bound, not again lower. So lower than the lower bound, but upper than the upper bound because they have to exceed the upper bound for it to be considered as an outlier. Then re-execute. Then indices. So you have the same. Yes, John.
sorry, I muted by mistake.
Okay. Is everyone's code running before we can save the one without outliers? So I proceed by show of thumbs up. Yes, yes, be there.
Kindly, you can paste for me the visualization bit here.
Okay.
Thank you.
Okay. Uh, Now let's save. Let's save now the data without outliers. Now, when you look at our detection right here, we did focus on the fact that for your data points to
Hi,
be
hi, Tony.
yes,
Are you sharing your screen?
I think so. Okay, let me share. Sorry.
Thank you.
Okay, sorry for that. So, if you look at how we detected our outliers, we were on the focus that your dataset has to be less than the lower bound and also upper than the upper bound. Now, for us to be in the case scenario whereby now our data points are in between, that is the lower bound and the upper bound. So it means that our data set has to be greater than the lower bound, but now less than the upper bound, so that we can be in the spectrum of the between the maximum and the minimum from layman's point of view. Now, then from there, after doing that, we need to save our data. So you have to save the data or rather create a copy that now you move forward to making use of it. So this can go about whereby you can decide and change and or rather make use of this same line of code. Then you can add the lower and the upper, whereby you make use of the greater or the less equal sign. So for our case here, we are going to add, try to modify this. We see without the indices and everything. Uh, so right here we can make use of can make use of the all of this. Still be on the right track. So just copy that code the way it is, then come to after the visualization, then paste it, then let's edit. First of all, we don't need the indices because the indices were there to show us which column has which number of outliers. So delete that there. Then whereby we have the outlier to indices, also get rid of it. Then also here in the case of the print whereby we made use by the length, also delete. So our focus now it's below here whereby now we are focusing on the cleaned data set. And for us to focus on the clean data set, now where we didn't delete our indices is whereby now we're going to create our copy. So we'll have, let's say, data underscore cleaned equals to data dot copy. So have it right there. So the dot copy will copy the data. Then whereby we have our outliers now. I want you to change this to be, let's say, data. Can go with data underscore cleaned. Yeah, data underscore cleaned equals to now your data being greater than the lower bound and less than the upper bound. Then now here we return our data underscore cleaned. So I'll move here, the same code of cell. We don't have to go to another code of cell. Then now we define the clean data without outliers. Then we'll have something like that. So because we had created a different one, so we can have this with a new variable name. Let's say remove underscore outliers. Make it self-descriptive. Have your variable names to be self-descriptive. Now we refer to it as remove underscore outliers because we already have another variable name with the same. So we're kind of reusing because it's the same logic our function has to use. And then we can have here our data underscore cleaned and see whether it works. So we have our remove, put in a copy, so here we forgot our data underscore cleaned, select columns, content range. So here we're working with, sorry, forgot this, data underscore cleaned, data underscore cleaned, which is the copy, don't forget. And here again we're focusing on data underscore cleaned. Sorry for that. And then here underscore cleaned. And here underscore cleaned. Let's see. Yeah. So this is it. Yes. You should be having something like that. So we can be able to inspect the first 5 rows and the bottom 5 of our cleaned data set. We should be indexing. Yes, John.
When we're getting data cleaned, should it be or or and?
And this one, but have this. It should be on the shift of the backslash.
Yes, so no, I was asking for the condition. Should it be and instead of or?
Yeah, and because if you give it an or, then you're giving it an option of both. So it should be both. And so the lower bound has to be, all the data points have to be greater than the lower bound and greater than the lower bound and less than the upper bound. It should be and. You want to replace this with and.
No, I was just asking because I'm seeing we're getting the same. We still have the number of the same. The shape. The shape has not changed.
Yeah, it doesn't change. So I'm trying to figure out where our function is wrong. I've also noticed.
So that's the reason I was asking. Should it be or and?
It should be and.
Because in our formula it's or.
Now formula it's all. Okay. Same. Same shape still. Okay. So let's inspect.
The shape has actually changed if you run the second line.
Okay. So initially we had, yeah. And the shape has changed. So everyone to correct this one shouldn't be or. The or is this one. So change it to and. Thanks for that. So if we check for the shape, we get how many rows and columns? 16 to 31, and we had minute. Yes. Yes, Rashid.
After changing to and, I'm getting a warning. Boolean series key will be re-indexed to match data frame index.
Let me see. Yeah.
Okay.
I'm not sure of that one. Maybe what it's trying to say is the indexing. You can see my indexing is 3. It's not consistent because I didn't have the false part. Maybe that's what it's trying to communicate. the indexing of the data frame, whereby you have the rows. Maybe if you can just have the data underscore cleaned dot head, we see in a new cell, just a new cell. Then we see if it did the reindexing dot head. Yeah, see, it didn't do the reindexing. I think that is the warning. Nothing else, because the code is okay. Anyone else? Anyone else, please? Okay, so let's proceed to the linear regression model part. Okay, so let's import the necessary libraries for linear regression model. So we're going to start with what we're going to get from the skitlearn. And from the skitlearn, I'm going to get our train, test, and split, which is responsible for training, testing, and splitting our data set into the 20-80% rule. So we'll have from sklearn dot model underscore selection import train underscore test underscore it, and then from sklearn dot linear underscore model, we get to import now the linear regression model itself. So linear regression model itself, and then we have to get the metrics. So from sklearn dot metrics, I will import the mean squared error and the R2 score, and execute. From sklearn and the linear regression. Yeah. Okay. Now, from our data frame right here, we can be able to tell that when we are defining our feature vector and our target vector, of course, now the target here, which is the price, is the one that will be dropped and be replaced in your Y. So we define the feature and target vectors. So we'll have our x equals to df. So I will pick all the features except now our target, whereby I'm going to drop it in the axis equals to 1. Axis equals to 1 simply means that focus on a column. So we'll have df, no, not df, we'll have data, sorry, our df, my head. So we'll have here data dot drop target, then replace it in your ML models have to have the feature and the target variable. Okay, So after doing that, you proceed by train and test split of the data. So you start by defining your X train. So you'll have X train, comma, X test, of course with the underscore because those are two words. Y train, comma, Y underscore test. Then we'll have the train underscore test underscore split coming in, which is responsible for splitting our data into the training and testing sets. So we'll have train underscore test underscore split. So what are we splitting? We are splitting whatever that is stored in X and Y. So we are splitting X, comma, then Y, comma, having our test size being defined to be 0.2. So by having it at 0.2, meaning that I am already training at 80%, then having my random state for the shuffling being at 42. So split. Then here now we train the linear model. So we train the linear regression model. So I'll give it the variable name model equals to linear regressions. First of all, I'll have to initialize it. So linear regression with the parentheses, that is the circular brackets. Then I will fit the model to my train and X train and the Y train. And execute. Okay. Now remember when I'm training, I did get to split, that is the training and the testing sets. So I'm able to evaluate the model by making use of the portion of the data set that I had beside, that is for the testing, so that I can be able to determine when the values were at this point and it's predicted at this, was it some sort of like an MSC, that is the mean squared error, was it high or was it low, for the same as the R squared, which should be always moving towards 1 to show a better fit of the model for your data set. So we make predictions so that we can be able to evaluate. So make predictions whereby we have our Y underscore predict equals to model dot predict, and we're predicting our X test. Okay, so determine our Y predict. Then we do the metrics at this point. So for the metrics, I'll start with the MSC, which will have our mean underscore squared underscore error for the Y test and the Y predict. Then our R2 score will have R2 score for the Y test and the Y predict. Execute this, then you can print the MSE, that is the mean squared error, and the R2 score right there. So the mean squared error should always be as low as possible, and the R squared should always be moving towards 1 to show a better fit. So who can tell us why we are having the 0.55 and the 0.57? Somewhere. Rashid, why you think we're having a very high MSE and an average R squared? Joan? We didn't use our cleaned data, but our clean data was under bit underscore cleaned. So we can see when we make use of the data underscore cleaned what happens. So here is you can have this as a model training with outliers, so you can see the difference. And then you can have here the model training without outliers. We keep the same, you can click that, just change the variable name. So remember Python is case sensitive, so I can go about with the caps X and the caps Y that way, then stick here to have it as underscore cleaned. Then here also underscore cleaned. Execute. Split the dataset the same way. So stick to caps now to differentiate the variable names. Change this. Initialize your model and fit. So you will have that. You will have that. Then come about and do your predictions. You will have that. You have that. That. Then print. Has it gotten any better from the two observations of outliers and without outliers? Be there? Has it gotten any?
I kind of got lost long time, so I'll just follow later.
John, has it gotten any better?
Yes, it has reduced. The mean squared error has reduced.
So does it mean that regression models are prone to outliers? They're being affected by outliers?
Yes.
Yeah. So that's how you go about a simple linear regression, yes?
I had a question where we trained the data for random state. Should it always be 42 or does it make a difference when you change this value, or should it always be random state is equals to 42?
So when you keep it at 42, you're kind of keeping a reproducibility. so that when every time you come about and rerun the notebook, you get the same results. So it helps to shuffle the same way it shuffled in the initial time when you created the splitting. So you get the same. Anyone else? Okay, so that's it for today. Tomorrow we cover the ridge and the lasso regression, the same, and also the logistic regression using the same data set. Okay, so that's it for today's class.